Omar Costilla-Reyes es científico e investigador en el grupo de investigación Computer Aided Programming. Dicho grupo es parte del Computer Science and Artificial Intelligence Laboratory, CSAIL, y presidente del AI Latin American Summit Initiative, ambos en el MIT. Cabe resaltar que conocí a Omar ahí en ese evento, así que muchas gracias, Omar, por aceptar la invitación. Generalmente, el objetivo de la investigación de Omar se centra en el desarrollo de la programación de proyectos neurosimbólicos y la interpretabilidad científica para la salud mental digital. El descubrimiento matemático, la codificación del conocimiento experto en física y la ciencia cognitiva computacional para la educación personalizada. Omar, es un placer tenerte por aquí y la pantalla es toda tuya.
Bueno, muchas gracias por la invitación. Primero que nada, voy a dar la plática en inglés porque traté de hacerlo en español, pero es muy difícil porque todo lo que trabajo está en inglés. Entonces, lo que podemos hacer es, hago la plática en inglés y toda la discusión si quieren la hacemos en español. No sé, también pueden conectar o Spanglish, no sé.
Está bien, hagámoslo en Spanglish. Gracias.
Pero bueno, ok, vamos a empezar. Entonces, bueno, muchísimas gracias por la invitación. Hoy les voy a presentar un tema de investigación que se llama AI for Coding Science. Y sí, bueno, un poco de background de mí. Yo soy de México, estudié licenciatura en México y he estado ya en el extranjero varios años, haciendo mi maestría en Texas y ahorita ya estoy pues, en el MIT como investigador. Eh, la investigación que les voy a mostrar hoy pues ya tiene varios años. Estamos trabajando por parte de un grande National Science Foundation y espero que pues les guste los temas que estamos trabajando y si tienen preguntas pues pónganlas en el chat o díganme y sin ningún problema trato de contestarles y también espero tengamos tiempo al final para un poco más de discusión. Bueno, entonces voy a hacer ya switch to English. Okay, so we're going to have three parts for this presentation, right? So the first part is going to be the symbolic component of my research. Then the second part is going to be the neural component, and then I'm going to give you an example of the techniques, right? So the first two is going to be just an intro of these parts of what I work with, and then at the end, hopefully I can connect these two into a single example, so you can understand what is the meaning of everything that I'm about to present. So first, let's start with the symbolic part. So I wanted to first make this analogy with the languages of the world, right? So one of the things that we have in all of us is we share different languages for expressing our culture, where we are from. From Mexico, you guys are from Peru, so even though it's the same as Spanish, we have differences in languages, right? So I wanted to first give the perspective into this this way of thinking about language first, the perspective. So then I wanted to also mention that I wanted to say how do we communicate with computers, right? So that's one of the most important questions that we have in computer science, and that's the whole field of research of human computer interaction, and we want to express what with the tasks that we want to do for the for the kind of goals that we want to attain with a computer. And so that's basically what we do in our lab. We try to understand how we can translate the goals that we want to achieve in computer science and how we can express that in code, right? So that's basically the job of a software engineer, if you ask me, right? But we go a layer deeper into the meaning of how to do this, right? I'm going to be centering in this talk about how exactly we do that. And so to put the context of programming languages research, which is what we do in our lab, you can just think about Python. So Python is a programming language. And basically our lab and our research, what it tries to do is to design, implement and analyzing programming languages to make them more effective, efficient, and easier to use, right? So that's the whole objective of our research and what we want to do, in our lab. So there is also different areas of research that we can focus on. So one of them is type systems, domain-specific languages, language design, compiler, right? So you can go in very different directions of the meaning of what is a programming language and what you want to research on this kind of topics, right? So for the purpose of this presentation, I will only focus on domain-specific languages. But there's all these other areas of research that you can, go and learn more about, how can we do research in this very specific area of computer science. So first, what is a domain-specific language? A domain-specific language is a specialized language for a particular application domain that, in contrast to a general purpose language, is broadly applicable, which is broadly applicable across domains, right? So we don't want to do that, right? So we want to be very specific, and we want to target that language for a very specific task, right? So here you have a very simple example, right, of how you have two variables, right? So in one of them you have a select first name, last name, and then for employees where salary is this, right? So this is a SQL code where you have this variable for employee, and then you're trying to select, from the first and the last name, and you want to filter by the salary, right? So this is a very succinct example of a domain-specific language, because this is how we go from a general purpose, open-ended language like C++ to like a very, very specific variable with a very, very specific type of variables. And I'm going to explain you why this is useful in a second. But before I do that, I also want to clarify what is a program, right? So, at the end of the day, we study programming languages in order for us to understand programs, right? And you can also understand program as a form of computation, right? Description of how to perform a computation. And when we study programming languages, we study programs, and the properties of programs are divided into two. So we have a syntax, and we also have semantics. The syntax is just the grammar, so what I showed you before, like the actual words, right? And then the semantics is the meaning, right? So what does it mean? For example, in the previous thing, you have first and last name, right? So that's the meaning for those variables. And these are the two key components of programming languages. And then I'm going to be talking about synthesis in a second, but so in order for us to use these programs, we need to take care of the expressiveness of these domain-specific languages, which I also will explain in a second. What do I mean with this? So first, to give a little bit more of context, I wanted to, hopefully all of you have some kind of background in machine learning. So if not, so feel free to ask me, but this is decision tree, right? So, well, it's not very hard to explain. So you don't actually need to do machine learning to understand this. But, so decision trees, what they basically do, so they compose rules based on some kind of threshold. So in the left side, you can see that we have male, age, certain threshold, and you can make decision yes or no. Right. So for us, another way you can look at this decision tree is kind of like a program. So at the right side of this of the screen, you can see how we can express the same kind of structure, the same kind of tree, but now in a very programmatic way, right? Which is the kind of research that we do in all that. So here you have if, then else statements, they also return statements, right? So it's kind of like the same kind of role, right? So for us, decision trees is a very specialized language. And also they are very similar to the goals that we want in our lab, right? So what we want to do is we want to learn from data, right? So decision trees learn from data, so it's a machine learning algorithm. But at the end of the day, what you learn in decision tree is a program. Right? And that's basically what we do. So, well, at least the research that I do. So we're trying to combine these two areas of research where in one side you want to learn from data, but on the other side you also want to express that as a program instead of just having For example, like a deep neural network is purely like a black box model. So the reason why we want to do this is because programs offers us much granular level of interpretability and also to explainability for the kind of things that we want to understand, which in this case is science, but I'll go into that in a second. So as I said, program synthesis is kind of like a decision tree, right? So in this case, we look at this as like a top down, right? So you start with very few assumptions from the program, and then once you go down the tree, you can start composing more complex programs down the line, the expressiveness of what we're looking for. We build algorithms that go and search in this space of programs, which is very similar to a decision tree. That's the reason why I started explaining you with a decision tree, because for you're doing some kind of machine learning, for you can get the meaning more easily than if you like to jump through. Because this is a very specialized area of computer science, and if I jump with other examples, we'll probably get lost. But I hopefully with this example is pretty clear, like what kind of research we're trying to do. So from programming languages, so I have taken you by hand, or like we started with the meaning of programming languages, program, decision tree, and then I can introduce you the very specific area of research that we work on, which is program synthesis. And so when people ask me, in a party or anywhere I go, like, what do you do? Nowadays it's pretty easy to explain what program synthesis is, because everyone understands ChatGPT, and most of you have also probably actually did write a program. So that's basically what we do at the high level. So instead of software developer writing line by line what you want to do in the program, you have some kind of high level specification to generate the program. So you want to generate it right rather than writing it. So before ChatGPT, it was very hard for me to explain every reason, because it took some time for people to get it. Now, with ChatGPT, everyone knows, what I'm trying to say. But we were working on this way before like language models, and for us, it's a very different approach of what these systems do, and I'll also explain why. So this slide was more about like be very specific of the kind of techniques that we use. So you can, for example, use logic, some kind of deductive synthesis, where you try to deduct like what specific parts of the program you need, and then at the end of the day, we want to generate the actual program, right? Which in this case is using like C code, and like also like a proof that for that specification at the beginning, right? Which in this case is logic. But this is not the only way, right? So we have many other ways of doing this, right? So one of them is like input-output examples, right? So this is very similar to machine learning, where you have like the input data and the labels. It's very similar to this approach. As I said before, you can also do logic. You can do something called equivalent programs, natural language. For example, the case of ChatGPT, or ChatGPT is a natural language approach to the problem, right? And then we have some kind of search space, and then you can see here the concepts that I told you before, right? There have some kind of grammar, we have a DSL, we have some other components, and then at the end of the day, you create a program out of this. So when you work on this space, so this is the very specific area of research that we work on. And when you are in this area, you need to balance three things. Right? And this diagram kind of shows you the very concrete ways, things that we need to balance as researchers in the studies, right? So in one side, we have the user intent, which is, how people want to, what they want to achieve, like the user, like what do they want? What the user is trying to accomplish, right? For example, when you write a program in ChatGPT, when you ask ChatGPT for a program, did you specify the right way? Do you have the right intent to generate the program that you want? So that's one of the things that we care about. On the other side, we have a search space, right, which is where we're going to explore the type of the programs that we can obtain. And then we also can have like a search strategy, right? So how are you going to organize with that specific program that you are looking for to searching, right? right? So another way, so I already explained about ChatGPT, but there's also the example of Copilot, right? So I'm not sure if any of you know about this program. It's also like an add-on that you can have in Visual Studio or any kind of IDE that you use. And the idea is that you write some kind of part of the program, and just let the thing infer the rest of the code, right? So this is another form of synthesis, but again, it's a very this is focused on what I said before, which was large language models. In our case, we're not doing, but here's another very clear example, right, on like what we need with program generation, which is the case of Copilot and what they do there. So just this slide, it kind of like summarizes everything I've taken you explaining you so far, right? So in one side we have the input to the system, right? So what do you intend? How do you represent the domain knowledge? And then you have two different constraints, right? The behavioral constraints, which depends more in the user, like what the user provides. And the other one is the structural constraint, which are actually the program itself, right? The DSL. What are you trying to find in terms of primitives? What is the space of program that you search for? And then, the program synthesizer is what you go after you have these constraints, this input intent, and then you can, at the end, obtain, the code of program that you're searching. Okay, so that first part for me is kind of like a symbolic part. And literally, when I talk about symbols to people, sometimes they're confused. But this is what I mean with symbols. So this is symbolic. Everything I showed you before, a program is symbolic, right? It has variables, it has some kind of rules, logic, and we kind of understand, right? And on the other side, we have neural networks, right? Which is, that the other area of research that everyone knows about these days. And yeah, so this is the part 2 of my talk. And so I wanted to start first on this comic that I think it's called XKCD. Yeah, so it's I should put it for the next time. But this comic, makes a very nice assumption on like a very good analogy of what machine learning actually is, right? So here are these two guys, they're talking, and one is sitting on top of a pile of algebra, and the one of them is asking to explain like what is machine learning, and the other guy says just pour data in, and then once I can keep steering this part of linear algebra, I'll get the answers that I want, right? So that's actually a very clever way of thinking of the system, right? So just kind of like modifying weights and modifying internal things, and until you find the answer, right? So for me, kind of like the meaning of the pile for me means that you don't actually know what's going on, right? Which is in comparison with what I showed you before. Everything I showed you before is very interpretable. You can read it. You can go line by line, and you can just go and read the program. Right? In the case of neural networks, we can't do that. So it's pretty hard to understand what's going on. I mean, there's a very active research, like trying to understand like what the neural networks are doing. But at the end of the day, the file for me is kind of like a black box, right? We don't know what's going on, and we just kind of like depend on these inputs and outputs, and then we're more or less hacking our way to finding the solution that we want. So as you can see, this is another way of looking at the neural network. You have your input layer, input data, and then you have your output layer, and then you have these hidden layers in between, trying to find these correlations and these different types of correspondence between the input and the output, and then you do backpropagation, which is very fancy algorithm that got Jeff Hinton the Turing Prize. But anyway, so the other thing that has taken the world by storm is this transformer, right? So in this case, we have basically an encoder and a decoder. So where these things are coming from is from human translation. So the language translation. So in this case, we have the input, which is French, and then we want the output to be in English, and then we use these encoders and decoders to help us arrive to this solution rather than Obviously, this is a much more complicated than this. But yeah, this is the basic essence of like transformers and what's happening today in the world of AI. So going back to the point that I made before, right? So now you kind of like have to have explained both of the um, techniques we're interested in. In one side, we have symbolic programs, which are very interpretable. They can be verifiable. They can incorporate domain knowledge, and they can be data efficient. So these are the benefits of symbolic programs, which is what the first part of the talk. And then the second part, we have focused a little bit on neural networks, right? Which the benefits are that you can scale them, right? So they can work in by basically the internet, right? So now I can really say that you can train them on the internet because that's what people are doing today. They're pretty flexible, you know, they can handle a lot of noise in the data, and they're very easy to get started. Right? So anyone can learn, you know, machine learning in a week. Well, at least the basics, right? So I think it's very good starting point for people, right? So I think those are kind of like the benefits. And in my research, we're trying to bridge these two techniques. Right? So the lab I'm coming from, you know, my lab has been traditionally focusing on symbolic programs and symbolic research. And when I came, we started thinking about more like how we can augment our research and go more into like the neural network point of view of this research, right? And try to bridge these two if we can. So as I mentioned before, here's another. This table is just basically what I showed before, but it's kind of like comparing, you know, the conventional ML and the synthesis approaches. And so this is actually how a DSL looks like, right? So you remember we started thinking about DSLs. So in this case, we actually use DSLs as well. And this is the way we express them. And this is how a program actually looks in the domain-specific language. And, you know, it has a set of properties that we can use. And this is, you know, what we use to express the type of program they're interested in. And so, you know, so linking this to the title of my talk. So, right, if you remember the title of my talk is AI for code and science. So I think I already covered the code, right? But I still need to explain you where the science is. Right, so our lab has been working on systems that actually bridge this knowledge, right? So on one side we have the symbolic representations of programs, and then we want to go from there and find actually useful symbolic programs that can be used in science, right? So the case that you see here in this system that we call DreamCoder, which learns these libraries and these functions, is for a physics problem. So as you can see here, is just kind of like add vectors and then inverse squares. So all the variables that you see here is actually a physics problem, a physics representation. Right? So you start with some kind of primitives, and then you want to go and learn more complex problems at the end. Right? And then here you have also another example, which is in chemistry. Right? So in chemistry, we have all these nodes and all these relationships, and we can actually build programs that study these relationships. Right? So in this case, you know, you can see where the domain-specific language comes from. So all the variables that you see here on oxygen, carbon, nitrogen, anchor, all these things can be expressed as a domain-specific language, right? Because these are the only variables that we care about, right? And if we want to find a symbolic program that you know, kind of solves a problem in this space, you know, it's very important for us that it has is able to capture these different variables and that type of problem that we're interested in. So yeah, so just to explain a little bit more like what is neurosymbolics. So we have as I already said, like a neural symbolic element, right? And in this case, for example, you can build a program that understands digits, right? And kind of like find a symbolic solution that can do that. You can also build controllers, you know, instead of having a neural network, pure neural network controller, you can build one that has some kind of verified policy, right? So the verified policy is to be able to be safe, right? So safety is another area of research where we're interested in. And in this case, we're trying to make sure that the algorithm doesn't do an incorrect thing or an unsafe move. And you can do that also in like a symbolic expression of the program. And so here it's a very specific example on a program from a project that we've been working on, which is in the neuroscience domain. And here we're simply trying to classify actions between mice, right? And we have all these variables in these primitives that study the distance and the acceleration of these mice, right? And we're trying to find this type of programs and program parameters, right? So these program parameters look very similar like weight in neural networks, right? So yeah, they're learned that way because we use neural networks to learn these programs. But at the end of the day, you can see that they're just kind of like a constant, right? They are not weights for solution. They're just expressing a constant in our variables, which is at the end of the day what we're interested in finding. So yeah, so this is one example. So I don't want to get very deep into this one because another example hopefully we can spend some time at the end. But happy to chat more if you have questions. But yeah, so this is the structure of the programs, right? So we have some kind of input. We have algebraic operators, parameterized operations, right? So the parameterized operators, this is where the neural networks come in, right? So you can see that it's kind of like a weight here. So this actually can be learned from a neural network. So, you know, this is another way of looking at the problem, right? So you can have data as an input, the structural constraint that I talked before, right? And then you have this learner, and then you have some kind of function here that helps you find this program, and then you have this if and else, and then you can calculate how you can satisfy the constraint and find the program that actually solves the problem that you have. So you can see here like the inputs, the outputs, and the type of solutions that we're looking for in this specific area of research. So yeah, let's just keep that it's not that important because I wanted to spend some time in the example, right? So so this is one of the projects I'm very excited about, and hopefully this one will give you a very concrete thing of what I've been talking about, right? So because it might feel very hard, or you know, I hopefully with this example, I'm able to you know, make the point of why these things are important, right? So one of the things I'm very interested in is in the domain of mathematics, right? So I mean, my interest in mathematics is in two directions. First, I think that a lot of the research in mathematics should be automated, and it's not automated today, right? So there is these mathematicians spending all day and night just thinking about problems in math. But for me, it's kind of hard to believe that this is the case because, you know, mathematics is quite a precise discipline, right? So why do we need mathematicians that spend 10 years to write a paper while we have a very constrained and very specific set of rules in math, right? So math is not kind of like the social sciences, right? So which we don't know what we're doing because I'm also doing social sciences. But math is very precise. Right? Math is not that if this or not, or like it's not subjective experience, you know, no. So math is very precise. So for me, it's kind of surprising to know that math has not been automated. So if you think about that a bit deeply, it's kind of hard to believe that it's not the case. So that's one of the motivations that I wanted to study this domain. And the second motivation was because I think that if we can automate it, then we can also maybe have an impact in education, right? So we can teach these kind of concepts better, and people who actually understand better how to do math. One of the most challenging subjects that we have in the sciences, right? So people hate math. So how can we make it more easily for people to understand? So that's the second motivation that I have. And so yeah, so we expressed this problem that I'm presenting here is just solving linear equations, and we go step by step. You know, kind of like you start with this at the right, you know, and you start breaking it down until you find the solution. This is the basic problem that we are stuck, right? So you have a linear equation, And then the idea is how you can break down this in order to find a solution. So the other surprising thing when I was studying this problem at the beginning was also I could not understand why this was not automated as well, because it's a linear equation, right? So why don't we have systems that you can take a linear input and then find this x equals this, right? It was hard to believe as well, but it's actually a hard problem. There's no a specific system that could take you any kind of linear model and then find you the precise solution in very step by step. Sometimes it cannot find the solution for very specific problems because sometimes the relationships or the kind of operations that are being done are very, very specific. And it's hard for the system to actually solve this problem. So in this case, we need to use reinforcement learning to be able to solve that problem. So we formulate this problem as a contrastive learning problem, right? And the idea was just to kind of like do some kind of beam search, right? So kind of like a smart search to take all the alternatives in the search of the solution, then train a policy that maximizes the probability of picking successful decision of an alternative solution, right? So what this basically means is that we start with the equation and then kind of like brute force, kind of like taking it step by step, see we arrive to the correct solution. And we have a smart algorithm that can look into the right search tree, right? Because as I showed at the beginning, everything we build are trees, right? So you will go down a tree exploring, right? In this case, we're exploring the solution. Right? So if you want to do it like brute force, it will take you, I don't know, like forever to find the right solution. So we came up with this beam search, which is like a more intelligent search in order to arrive to the right solution. And then these are the steps. So you can like initialize the policy, then you do the beam search, then you alternate with the negative examples, then you do this info and C loss, which is, I won't go into detail. It's a very specific type of loss that we use here. And then you repeat basically step 2 to 4 until we find the correct solution. And this paper was published in 2021 in years. And it was, led by our collaborators at Stanford. And then, like the data set that we use is called the Common Core. It's kind of like a data set of equations that people use in grades 9 to 12 to teach math. And we just kind of like scrapped all the equations from the book, and then we put it into this learning algorithm to try to find the correct solution to this problem. And so here are the results, but then the second part. So the first part was kind of like setting just the stage. And then the second part is kind of like, it kind of clarifies where this symbolic and neural network comes into place, right? So in one side, we have the steps that you need to take to arrive to the solution. So you can see here that we start with this, and then we start moving the equation, moving the numbers, and then at the end, we arrive to the solution. But, so these are the actions that we use, right? So as you can see here, I forgot to do this, but actually the algorithm, in order to arrive to the solution here, the algorithm takes at least like 20 steps. What I show you here is the simplified version, but the raw data, it takes at least like 20 steps because there are many things that the algorithm has to do in order to apply the actions and to arrive to the correct solutions. It's a simplified way. And what we want to do is to abstract what was important, right? So the idea was to go from these like 20 lines solution and then abstract what's important. And then at the end of the day, use those abstractions to be able to be reused in the future when the algorithm sees these patterns in order not to be like also dumb, like searching through the entire space and, go step by step what we know, right? So the idea is to, if you know a pattern of search, abstract the pattern, and the next time the algorithm goes and search, it will keep searching all that part. Because now we have this very simplified way of like skipping that. So that helps you in training time and, like how long this arrives to train and so here are the kind of things that we find. So these are abstractions that we search in the algorithm, and this is how we apply the actions to be able to make this be interpretable. And here, the plots, you can see the blue lines. The blue line here is the original system, right? So the original system didn't use any abstractions, right? Just like, as I said, like just apply this smart beam search. But at the end of the day, it went through line by line, right? Just applying each action, and until you find a solution. And then when we apply this abstraction, which is this pattern abstraction of the steps, then as you can see here, that we arrive faster to the solution, right? Because now, since the algorithm is learning the abstraction, we can go and learn the solutions faster, right? Compared to the other algorithm, which takes pretty long to arrive to that, right? But if you see the steps, this is still a lot of steps, right? So we are talking about 10 million here. So yeah, and so this is all the steps that it takes to arrive to the solution that we want, because it's important to learn. So it takes a long time, and but this is a positive result that we got in terms of like combining these symbolic expressions, right? So in one side you have the abstraction, the algorithm that applies the actions and find the abstractions. All of that is symbolic, right? And the reinforcement learning agent, right? So the agent that's actually searching is neural, right? So here is kind of like the combination of the two techniques that I just explained, and this is work that we published last year, and you can find it online, and I can share with you if you're interested. But yeah, so that's pretty much it. I mean, we kind of like I hope we ended up on time, but yeah, so this is more or less what I wanted to show you, and happy to chat. I mean, we can switch to Spanish now if you want, because. But yeah, so I just wanted to give you guys an overview and an example, which hopefully helps clarify the area of research that I'm working on.
Muchas gracias, Omar. Es súper interesante. Y seguramente algunos de nuestros estudiantes también han podido reforzar algunos conocimientos que ya tienen en Machine Learning y entender un poco las diferentes direcciones de investigación en este tema. Bueno, si alguien tiene alguna pregunta para Omar, puede levantar la mano o desmutearse, hacerlo en español o
Creo
en
que en el chat,
inglés.
¿no? Creo que hay varias en el chat, ¿no? Varias preguntas.
Sí, déjame leerlas para ti. A ver, Alfredo Yupanqui dice, el audio no es claro, pueden subir el volumen. Bueno, también podemos encontrar las grabaciones en las páginas de la carrera de Ingeniería Informática. Tal vez si es que alguien no puede entender muy bien el audio. Buenas noches. ¿Cuáles son algunas aplicaciones? José Manuel Ames pregunta, ¿cuáles son algunas aplicaciones notables de la inteligencia artificial en los campos del desarrollo de código y la investigación científica?
Pues creo que ya lo explicamos, ¿no? O no sé si fue la pregunta antes de que explicaremos un poco, o no sé si hay algo específico que quieran preguntar.
José
No, de
Manuel,
hecho, ¿por qué no mejor hablamos, ¿no? Porque es más difícil tratar de leer el chat. Entonces, si alguien tiene una pregunta, pues levante la mano o pregunte y adelante. Lo que quieran.
aquí hay una pregunta que me pareció interesante de Gilmar Oviedo. ¿Cómo se maneja grandes volúmenes de datos o cálculos computacionales en el código científico?
Sí, no, esa es una muy buena pregunta. Sí, ese es uno de los problemas principales que existen a esta área de investigación, en términos de que si nos vamos a la slide pasada que les puse como de summary, esta, o sea, un beneficio de neural networks es de que son scalable, ¿no? O sea, se puede poner muchísimos datos. Y en nuestro caso no. O sea, nuestras técnicas no son, o sea, no podemos poner internet en lo que hacemos, ¿no? Porque es muy difícil. Pero yo creo que esa es la idea de este proyecto, ¿no? O sea, tratar como de extraer de las redes neuronales datos que sean importantes y hacer como un embedding. O sea, yo creo que uno de los beneficios de neural networks es que hacen compresión, o sea, compression. O sea, todo lo que es neural network siempre hace una compresión de los datos, ¿no? Y uno de los de las cosas interesantes de Large Language Models es que estos embeddings que el modelo aprende, nosotros intentamos saber qué son, ¿no? Porque es algo muy complejo y muy interesante, ¿no? O sea, cómo ir desde el Internet a un embedding mucho más simple, ¿no? Más comprimido. Entonces, para nosotros es pensar ese tipo de estrategias, ¿no? ¿Cómo podemos nosotros estudiar, por ejemplo, los embeddings, ¿no? O cómo podemos nosotros combinar una parte de la red neuronal para hacerlo un poco más simbólico. En el caso de reinforcement learning, ¿no? Que les mostré al final, una de las etapas del algoritmo es hacer abstracción y hacer búsqueda, ¿no? Entonces, y la búsqueda se hace con reinforcement learning. Entonces, nosotros tenemos una forma eficiente de hacerlo con redes neuronales, la búsqueda con un agente de deep reinforcement learning y la abstracción y lo que estamos buscando es algo simbólico. Entonces, ahí está la parte que nos interesa a nosotros, que es la parte de entender esa relación. Y hay muchísimas maneras, ¿no? O sea, no es la única, sino que hay muchas otras. Por ejemplo, otra que les puedo explicar es, por ejemplo, algo que le llamamos distilación, que simplemente significa cómo podemos ir desde una red neuronal y tratar de pasarla a una expresión simbólica. Pues eso es también un área de interés, que es así literalmente, o sea, tienes un modelo black box y cómo podemos pasarlo a un modelo puramente simbólico. ¿Qué técnicas puedes usar para hacer ese como transfer, ¿no? O esa transformación? Entonces también es un área muy activa de research y obviamente no se puede hacer esto en Large Language Model, ¿no? Porque son muy complejos, son muy grandes. Entonces, cuando vas a esas dimensiones, ahí el distillation es como de 30 billones de parámetros a 7. Entonces sigues estando como que very high level, ¿no? Entonces sigues estando en una complejidad muy grande, pero bueno, ya menos, ¿no? O sea, ya no son más billones, ya son un poquito menos de billones. Entonces ese es otro ejemplo que también no lo mencioné, pero existe, que es el método de distillation.
Ujú. Genial. Creo que José Manuel aquí aclaró un poquito más la pregunta.
Ah,
Él se refería a cómo se utiliza la inteligencia artificial para mejorar los procesos de desarrollo de código de investigación científica. Tal vez la pregunta va más ligada a, bueno, nos mostraste que se está entrenando actualmente con, por ejemplo, un libro de ecuaciones. No nos quedó claro, bueno, al menos a mí, si era como del nivel de elementary school o primary school y qué tanto tal vez ya se está haciendo a nivel de la investigación que tú mencionabas antes de matemáticos, físicos que ya
ya.
estén haciendo cosas más, más
Sí,
elaboradas.
sí, no, esa es una buena pregunta. Fíjate que la respuesta es que estos problemas son muy complejos. No, o sea, entonces, o sea, si nos vamos a nuestro dataset es un dataset podrías llamarlo simple. O sea, es una grades named to 11, 12. Esas son las ecuaciones que leemos. Y o sea, imagínate que esto sigue siendo un área de research, ¿no? O sea, esto no está resuelto. Entonces, nuestra idea es que si queremos ir a ese nivel, ¿no? O sea, como que era un nivel mucho más avanzado, como ya ahora sí de investigación. Y, o sea, tenemos gente trabajando en eso. O sea, es algo que estamos pensando activamente, pero no podemos como que dar un salto así muy grande, ¿no? Porque hay todavía problemas muy básicos, ¿no? Que no se han resuelto. Entonces yo creo que la respuesta es no podemos pues brincar, ¿no? Muy rápido, algo más como que complejo porque la parte básica todavía no está clara. O sea, como estos problemas son básicos. Entonces, si todavía no sabemos cómo solucionar esto de manera eficiente, pues ¿para qué vamos a un problema de investigación? O sea, nunca voy a acabar. Entonces, la respuesta es realmente hay que saber desde una manera de first principles de qué es el problema y cómo lo podemos solucionar y de allí como que ir avanzando a cosas más complejas. Esa es como que la idea principal de research. Pero, o sea, esto es en matemáticas, ¿no? También en biología. No mencioné un proyecto de biología, pero también tenemos un proyecto de biología que está muy avanzado y también ya estamos planeando, bueno, el grupo ya está planeando en, pues, hacer un journal, ahora sí como que desde la parte científica, ¿no? De contribución científica. Entonces también es posible, no en esta área que les digo yo, no hemos encontrado algo ya muy avanzado, pero en otras áreas ya es mucho más fácil hacerlo. O sea, no es así que estamos igual en todos lados, sino para matemáticas estamos un poco más, cosas básicas, pero ya en biología ya tenemos resultados más interesantes.
Ujú. Bueno, otra pregunta por aquí de Sebastián Antonio. ¿Cómo se relaciona la IA con la ciencia?
Pero, ¿cómo? Pero
Sebastián,
más
tal vez quieres
específico, ¿no?
clarificar un poquito más la pregunta. Bueno, mientras esperamos que Sebastián aclare un poquito más la pregunta, Vanessa Nelsi pregunta, ¿cuál es el mayor desafío que afrontó en esta investigación?
Sí, no, esa es una buena pregunta. Es que, fíjate que eh, hacer síntesis, program síntesis, es un área muy difícil. O sea, nosotros, para hacer un problema interesante de program synthesis, o sea, un diseño interesante de un algoritmo, toma años de investigación. Es algo muy difícil porque es complejo desde la parte del search. O sea, tenemos que hacer un search muy complejo y tenemos que ser como muy inteligente en cómo haces el search. Desde ahí, ¿no? Desde ahí es el primer problema que tenemos es cuando buscas un programa en este tipo de investigación, explota, si literalmente, o sea, te puedes perder muy fácil. Entonces, como que es diseñar muy inteligentemente cómo podemos hacer la búsqueda. Entonces, eso requiere muchísimo tiempo, requiere muchísimo expertise para hacerlo de la manera correcta. Y, por ejemplo, antes de Large Language Models, las soluciones que nosotros teníamos en el mundo real eran más simples, ¿no? Por ejemplo, Flash Fill, que quizás no conocen ustedes, pero es la función de Excel que si tú pones dos líneas y jalas, te rellena todo lo demás. O sea, como que te rellena todos los números telefónicos o lo que quieras. O sea, es una forma de program synthesis. Pero eso era como que state of the art. O sea, eso era state of the art antes de large language models. Entonces nosotros vemos como que la parte de large language models como algo que nos puede permitir avanzar mucho más rápido esta área de investigación, pero también tiene sus límites, ¿no? Como lo mencioné antes, o sea, no podemos hacer investigación interesante en términos de interpretabilidad, porque pues, no nos dice nada, ¿no? Pero sí nos da un advantage en varias cosas, ¿no? Sí nos ayuda en muchísimas cosas, entonces es como que seguimos en eso de pensando cómo funcionan estos dos sistemas, ¿no? Desde una parte tienes las redes neuronales y desde la otra parte tienes la parte simbólica, entonces nuestra investigación es como tratar de hacer la mezcla, ¿no? De estas dos. Y en este caso, pues ahora es la language model. ¿Cómo lo podemos hacer en ese contexto?
Ujú, perfecto. La siguiente pregunta de Alessandro es con respecto a abordar estrategias de procesamiento de información alternativas a neural networks. ¿Cuáles son sus debilidades a la hora de procesar grandes volúmenes de datos? Quizá el aspecto topológico podría optimizarse. Am, Tal vez se refiere un poco a qué tipo de arquitecturas de deep learning se están utilizando mucho más en esta parte de...
Ah,
em,
ya, como que, qué arquitectura, ¿no? O sea,
ujú,
no, pues de hecho estas arquitecturas son muy simples, porque si tú vas al paper de Attention is All You Need, cuando ese paper salió, bueno, Attention is All You Need es este paper de Transformer, ¿no? Dice que ellos es el state of the art de esa área de investigación, de Large Language Models. Para mí, una de las contribuciones que ese paper hizo fue literalmente ya no hagan nada con Recurrent Neural Networks, ya no hagan nada con Convolution Neural Networks, porque literalmente ese paper destruye esos conceptos, porque no se usan, ¿no? O sea, ese Transformer no usa nada de estas otras arquitecturas que teníamos antes para cosas temporales, para imágenes. Y lo que dice el paper es simplemente necesitas atención, que es un concepto de machine learning, ¿no? ¿Cómo puedes poner atención a palabras? Y la otra parte es un feed forward, ¿no? O sea, simplemente lo que hacen es una red neuronal simple, no de esas ahora sí, de la que mostré al principio. Entonces, eso es lo único que necesitas. Yo creo que no, la complejidad yo creo que ya no es tan importante hoy en día, ya no es así que, no es que necesito este very specific kind of architecture, ¿no? O sea, no, eso como que ya no está, ¿no? Es más como, ya sabemos cuáles son las cosas esenciales y cómo podemos hacerlo que funcione en el contexto de nuestro interés. Entonces, yo creo que eso sí, pero tanto eso ya no, para nosotros ya no es de tanto interés, ¿no? Como tratar de encontrar una arquitectura.
Ajá. Bueno, ¿alguien tiene alguna otra consulta? Bueno, yo quería hacerte una consulta, Omar, con
Sí.
respecto a esa tendencia de que, pues, de que ahora con, por ejemplo, ChatGPT podemos ingresar un prompt que nos genere un código para hacer ciertas tareas. ¿Cómo tú crees que queda el rol de los software engineers bueno, en el mundo y qué habilidades crees que deberían desarrollar los software engineers para seguir vigentes?
Sí, bueno, es que yo creo que el problema no se va a ir, ¿no? O sea, siempre vamos a necesitar software, ¿no? O sea, yo creo que la diferencia es de que quizás ya no vamos a hacer tareas que consideramos nosotros hoy en día como que básicas, ¿no? Yo creo que las cosas básicas y simples ya van a estar. O sea, yo siento que la revolución de esto, de lo que está pasando, va a ir directamente a lenguajes de programación. O sea, lo que nosotros vemos hoy como lenguajes de programación, como Python y C++, se pensaron desde el punto de vista de nosotros, o sea, de cómo una mente humana puede entender estas syntax o lo que quieras tú del programa de lenguaje de programación para ser más eficiente, ¿no? Ahora imagínate que ya tenemos el Large Language Model. Entonces, ya lo tenemos. Yo siento que va a reescribir literalmente la manera en la que se escribe el software, ¿no? Porque ya va a ser otra manera de pensar el problema, porque ya podemos nosotros quizás ahorrarnos ciertos pasos, como el proyecto que les enseñé, ¿no? O sea, ya es como que ir así muy eh, brute force, ¿no? O sea, como que muy rudimentario, sino ya nos va a ahorrar pasos. Pero yo siento que el problema va a seguir ahí, ¿no? O sea, no es de que se vaya a quitar todos los software engineers. Y, o sea, para mí es desde la parte de código, ¿no? O sea, de generar código, porque ahora sí como que para deploy estos sistemas, yo siento que ahorita estamos en la etapa de que todos están muy emocionados y quieren ponerlo en sus empresas y todo eso, pero va a llegar el día en que van a ver las vulnerabilidades que tienen estos sistemas y los van a quitar. Entonces estamos como que ahorita en el wave de excitement, y ya cuando empiecen los hackeos y todo esto de que vean cómo se puede hijack y todos los problemas que tiene esto, ya lo van a quitar. Bueno, al menos eso es lo que yo pienso que va a pasar. Pero cuando tú generas código, pues es diferente, ¿no? O sea, no estás como que expose, no es como que el final product, ¿no? Sino que es como que un copilot, ¿no? Que te está ayudando a escribir el código. Pues yo siento que es más como desde la parte de que vamos a redefinir la manera en la que escribimos código, pero vamos a necesitar escribirlo de todas maneras, porque no es tan simple, no, no es así de que le pides a ChatGPT que te haga esto y ya está. No se puede, pero sí, yo creo que eso es hacia donde vamos. Y o sea, el pensamiento computacional, pues no se puede ir. O sea, yo creo que eso es fundamental, ¿no? O sea, entender desde un punto de vista científico cómo funciona un programa, que yo traté como de hoy tratar de inspirarlos a entender realmente cómo es un programa, ¿no? O sea, porque esto nunca se enseña, ¿no? O sea, todo lo que les mostré hoy no se enseña en cursos. O sea, literalmente tienes tú que trabajar en el área, ¿no? Para tratar de entender un poco más a fondo esto. Si tú pones en Internet Programming Languages, te va a salir Python, tutorial, esto, ¿no? Pero no te va a salir como que ahora sí, ¿de dónde viene Python? Que es como ahora sí como lo que nosotros estudiamos. Pero bueno, sí, eso es lo que pienso yo del tema.
Sí, coincido también. Y como profesora, creo que me llevo bastante de tu opinión también para discutir y para pues hacer un poco, evaluar un poco las medidas que vamos tomando los profesores también para la enseñanza, ¿no? Que también presenta como un reto todo esto. Enfocarnos en lo más
Claro, no, yo
importante.
creo que desde la parte de educación, pues Yo creo que el problema de plagiarism siempre ha existido. O sea, no es de que ya se hizo hoy con ChatGPT. O sea, o sea, en mi época, cuando era joven, se usaba Wikipedia, ¿no? O sea, te ibas a Wikipedia, hacías copy-paste de Wikipedia y ya sí presentabas tu trabajo así. Pero digo, al final del día, ¿quién se hace el problema, ¿no? O sea, el problema no es el profesor, ¿no? Ellos te van a poner 10, ¿no? O la calificación, el problema es tuyo, porque no estás entendiendo lo que deberías entender, ¿no? Y es lo que te va a servir allá afuera, ¿no? En el día a día. Entonces yo creo que eso es una pregunta mucho más profunda, ¿no? Realmente de pensar cuál es el propósito de la educación. No es así de que quiero pasar o de que ya, sino que, o sea, al menos yo creo que para mí me hubiese gustado tener estas herramientas para ayudarme a entender algo, ¿no? Porque a veces es difícil entender por tu propia cuenta, ¿no? Ciertas cosas. Y eso no lo tenía yo. Imagínate que tenía ChatGPT yo así como tratando de entender más y mejor y tener ahí como un tutor, ¿no? O sea, eso se hubiese sido mucho mejor para mí. Y hubiese sido muchísimo al menos para tutor, ¿no? O sea, para que me ayude a entender, no para que me haga la tarea. Entonces, sí,
Exacto. Sí. Bueno, muchísimas gracias, Omar, por venir nuevamente virtual a
sí.
Cayetano y queda extendida la invitación en cualquier momento para aprovechar una visita o bueno, ya estaremos conversando por ahí de todas maneras.
Sí, queda por ahí un chat, ¿no? Entre nosotros dos para ver qué estás haciendo estos días por allá.
Sí,
Sí. Y ya quiero
perfecto.
organizar otro summit de AI Summit, vamos a ver si nos pueden apoyar. También
Hace falta.
en
Sí,
Perú,
está
¿no?
bien.
En
Sí,
Perú.
encantados por aquí desde Cayetano. Hay algunos profesores también conectados, así que te tomamos la palabra y bueno, encantados de colaborar.
No, muchísimas gracias por la invitación y espero, les digo, mi interés de esto es pues crearles inquietud, que aprendan y que pues les interesen estos temas y siéntanse libres de mandarme un correo o algo. Les voy a poner mi correo aquí en el chat. Cualquier cosa, mándenme un correo si necesitan algo, pero bueno, espero que les interesen estos temas y muchas gracias por la invitación.
Muchas gracias, Omar. Nos vemos entonces pronto y nos vemos también con todos nuestros invitados participantes en cualquier otro webinar de la carrera de Ingeniería Informática aquí en la Universidad Cayetano Heredia. Hasta pronto.
Sí, bueno, gracias. Adiós.
Chao, chao, chao.